Welcome back to linear algebra and trigonometry. Today we are focusing on a simple yet powerful concept in the world of complex numbers, that is the conjugate. The conjugate is more than just flipping the sign of the imaginary part. It is a tool that helps us unlock deeper properties of complex numbers, from simplifying arithmetic to understanding their geometric behavior on the complex plane. By the end of this video, you will see how the conjugate plays a vital role in computations and why it is such an important concept in mathematics. Now, when we say the complex conjugate, or we can also simply call it the conjugate, let's say we have our complex number z is equal to a plus bi. Our complex conjugate can be represented as z bar, and all that you have to do is to change the sign over here. So in this case, we change from positive to negative. In other case, if for instance, if you have c to be equal to a minus bi, then this z bar, which is the complex conjugate, will be equal to a plus bi. So let's take an example. So we can have z to be equal to 3 plus 2y. So in this case, the complex conjugate is simply changing the addition sign to subtraction. So you're going to have 3 minus 2y. Okay, let's look at a different one. Let's say we have negative 5i. Now in this case, remember, negative 5i is the same as writing 0 minus 5i, where 0 is the real part. And if you are to change the sign to positive, the only thing you're going to do is 0 plus 5i, and we can just write this to be 5i. You can also have, say, z to be equal to 5. Remember, z is equal to 5 means you have 5 plus 0i. So changing the sign to negative over here, you're just going to have 5 minus 0i, which doesn't change anything, right? So you're just going to have 5. So that's basically the complex conjugate. Now, one thing that you have to notice, let's say you have, let me use a different color. Let's say you have z to be equal to a plus bi. There's our complex number. Let's verify that z double bar will be equal to z. So the key idea over here is, if you find a conjugate of a complex conjugate, you should get back your complex number. So in this case, let's say you have z to be equal to a plus bi, that is given, right? Then z bar will be a minus bi. In that case, if we want to find our z bar, we are going to just have, we just change this to positive, right? So we have a plus bi. So clearly you will see that this right here is the same as what we have over here. So it means that z bar and z is always the same. Let's take an example. Let's say we have 6 minus 7i. Let's try to see if that will work, right? In that case, you see z bar will just be 6 plus 7i. Z bar will just be 6 minus, change this to negative, will be just 6 minus 7i, and clearly these two are the same. Okay, so now let's look at some examples. Let's look at this question. If z1 and z2 are two complex numbers, we have to show that the first one is we have to show that z1 plus z2 bar will be equal to z1 bar plus z2 bar. Now to solve this question, we have to go through certain process, right? So let's first of all assume that our z1 is a plus bi, and our z2 is, a minus bi. So in that case, coming over here, right, let's just solve for z1 plus z2. z1 plus z2, we are going to have a plus bi plus, let me say, instead of a minus b over a, our z2 is just c plus di. In that case, we're going to have a plus c plus di, because these are two complete complex numbers, right? So they shouldn't be the same. So if we add these two, we can add the real part. In adding the real part, we are going to have a and c. Remember from the previous video, the real part is just a and c, and we have the imaginary parts. We see we have bi and di, and in this case, if we add them, we're just going to have b plus d. Remember, I just brought the I out. And now this is z1 plus z2. To find z1 plus z2 bar, all that we have to do is to change the sign in between them to the opposite sign. So in this case, we have a plus c, then minus I, b plus d. That is for the left hand side. Now let us look at the right hand side. For the right hand side, we know that z1 is a plus bi. So in that case, if we find z1 bar, we are going to get a minus bi. Now z2, we know it to be c plus di. So if we find z2 bar, we are going to get c minus di. So if we combine both, which is z1 bar plus z2 bar, we are going to get a minus bi, then plus c minus di. So in that case, we can group the real terms. So a plus c, then we bring the imaginary part outside, then we have b plus d inside the parentheses. So now comparing these two, clearly you could see that they are the same. So you've proven your results. I hope this is clear enough. Let's look at a different one. So let's say we have I. You have to show that z1 dot z2 is equal to z1 dot z2. So again, we are going to let our z1 be equal to a plus bi. Our z2 is equal to be c plus di. Then we find z1 dot z2. So to multiply two complex numbers, all that you have to do is to do it this way. So you do the FOIL method. So we FOIL it out. So first, FOIL means first to multiply the first term. So a multiplying c, we are going to have ac. Then a multiplying di, we are going to have plus a di. Then bi multiplying c, we are going to have plus bci. Then the last two terms will be plus bdi squared. So in that case, we are going to have ac plus, remember there's I. So we can factorize the I out. We have AD plus BC in the parentheses. Remember from our previous video, whenever you have I squared, this is the same as minus 1. So substituting it into our equation, we are just going to have BD, this one right here, times negative 1. And this is just minus BD. So we have negative BD to be our last term. So we have minus BD here. So now in grouping the real terms, we're going to have AC, then minus BD, and the imaginary term is AD plus BC. So now let's solve the right hand side to see if we get the same thing. Now on the right hand side, we have our Z to be A plus BI. So if we find Z1 bar, we are going to get A minus BI. Now Z2 is C plus DI. So if we find Z2 bar, we should get C minus DI. In that case, let us multiply. So we have z1 bar multiplying z2 bar, and in this case that is a minus bi multiplying c minus di. So doing the FOIL again, a multiplying c, we have a c, then this multiplying this, we have minus a di, this multiplying this, we have minus bci, then the last two terms, negative and negative multiply, so we have positive, then we have bdi squared. So doing the same thing, we bring the I out, we have AD plus BC inside the parentheses, and remember I squared is -1, so that leaves us with minus BD. So grouping the real terms, we have AC minus BD, then minus I, AD plus C. Now the question is, are these two the same? Remember this one was Z1 dot Z2, we have to find Z1 dot Z2 bar. So in doing that, we just have to change the sign to negative. So we have minus I AD plus BC. So let's compare. So comparing that to this, clearly you can see that they are the same. So you've been able to show your answer. Okay, let's move on to the next question. That is the third one. So for the third one, we are also to show that Z1 out of Z2 conjugate is equal to Z1 conjugate over Z2 conjugate. Now in this case, let us find our Z1, which is just A plus BI, our Z2, which is just C plus DI. So if we are to divide Z1 and Z2, we are just going to have A plus BI out of C plus DI. Now note, whenever you have division of complex numbers, to simplify, you multiply by the conjugate of the denominator. In that case, the conjugate of the denominator is just C minus DI, C minus DI. Note that if you cancel out these two, you have 1, and if you multiply 1 by this, that's the exact thing that you get. So you've done nothing, right? So we have Z1 over Z2, and that is equal to, so multiplying the numerators, you're going to have A plus BI and C minus DI. In the denominator, you're going to have C plus DI, then C minus DI. Then you FOIL it out as we've already done. So A times C, we have AC. A times minus DI, we have minus ADI. This times this, we have plus BCI. Then the last two terms, we have positive BDI squared. Then we divide by, so in the denominator, we have C multiplying C, so we have C squared. C multiplying negative DI, so we have negative CDI. Then this times this, so we have plus CDI. Then the last term will give you minus DI squared. Okay. So we can simplify this again. So if we do that, we're going to have AC minus BD. Remember, this will give you -1, right? So if you multiply by this, it should give you minus BD. This will be the real parts. Now let's simplify the imaginary parts. So you can have minus I outside, AD, then this should be negative BC. And we divide by, in the denominator, you're going to have C squared. Now note that these two terms cancels out. So you're just going to have, now minus DI squared is the same as minus D multiply -1, and this is positive D, right? Oh, sorry, this was supposed to be D squared. So in that case, we have plus D squared right here. So to find a conjugate, so Z1 out of Z2 bar. This one is just going to be changing the sign, right? So all that we have to do is to change the sign over here to positive. So we have AC minus BD, then plus I AD minus BC right here. Then remember, this is just the denominator. We just have C squared plus D squared. Now let us do for the other one to see if you are going to get the same thing. So on the right hand side, we have to find the conjugate of Z1, and the conjugate of Z1 is just A minus BI. Also the conjugate of Z2, this is C minus DI. So having a conjugate of Z1 over the conjugate of Z2, we have A minus BI multiplying C minus DI. Remember, whenever you are dividing, you find the conjugate of the denominator. So in this case, the conjugate becomes positive. And you FOIL it out. So you're going to have A minus BI multiplying C plus DI. Then you divide by C minus DI multiplying C plus DI. So if you FOIL it out, just as we did, you should have AC plus ADI minus CBI, then minus BDI squared. In the denominator, you're going to have C squared plus CDI minus CDI, then minus D squared I squared. So this simplifies to, now we have AC over here. If you simplify this, there should be positive BD. So this is plus BD. Okay, then if you bring the I outside, we can have plus I over here. So we have AD minus BC. Then you divide everything through by these two terms cancels out. So you divide everything by C squared plus D squared. So now comparing, did we get the same thing? So we have the denominators to be the same. How about the numerator? In the numerator, we have AC plus BD, and this is AC minus BD, AD minus BC. So it means that there is a problem somewhere. Okay, let's check the multiplication to see if we left something out. Okay, so right here, B times this should be negative BDI. So it means this right over here should have been negative. And if we do that, we should have this to be positive, because if we simplify this, it becomes positive BD. So this right here is positive. So comparing this to this, clearly we could see that our answer is correct. Okay, now let's look at a different subtopic. We call it the geometrical representation of complex numbers. So for this, we always represent complex numbers on the Argand diagram. We can also call this the Z-plane, or we can also call it the complex plane. So these are the same thing. Okay, so it always looks like this. Let's draw. So we have this. We have this right here. So we can have our A, our B, and have A, B. We can have the point where it means to be AB. Now on the x-axis, that is where we have the real part of the complex number, and on the y-axis is where we have the imaginary parts, right? So this is where we have the imaginary part of z, and this is where we have the real part of z. So this is what we call the Argand diagram. Now using this, let's solve some questions, right? First one is represent. We have 2 plus 3i minus 2 minus 3i, and then 2 minus 3i on the same Argand diagram. So let's do that. So first of all, let's draw our x and y planes. So let's say we have y plane, we have this x plane. So let's number, we have 0 here, we have 1, we have 2, we have 3, we have -1, -2, we have -3, we also have 1, 2, 3, 4, and -1, -2, -3, and -4. Okay, so let's look at the first one. Now 2 means the raw part is 2, so we have 2 over here, and the complex part is +3, meaning this is +3, so meaning that they meet somewhere here. If we draw the line, we're going to see that they meet somewhere here. So that's how it looks like for 2 plus 3i. Now for -2, -2 is somewhere here, and -3 is also somewhere here. So we can trace this down. So that's how it looks like, right? So we have this part to be 2, 3, and this part to be -2, -3. Now for the last one, we should have 2, so 2, this is +2, okay, and -3, -3 is here. So if we trace it, we're going to have something like this. So this is 2, -3. So this is how the Argand diagram is going to be like. I hope this helps. Okay, so let's move on to a different question, and that's the last question today. We have to represent the following on the same Argand diagram. So we have A to be I squared, B to be I cubed, C to be I to the 14th power, D to be I to the exponent of 25, E is I to the exponent of 28, G is I to the exponent of 31, then we have I to the exponent of 1985. Okay, so first of all, before we do this, we have to find the coordinates of I squared and so on. So let us first of all do for I squared. Now I squared, remember, I squared we know is just -1. So in coordinate form, we are going to have, this is the same, right? -1 is the same as saying -1 plus 0i, right? So we can just represent this as -1, then 0. So the real part is -1, the complex part is 0. Let's move on to the B. I cubed is the same as I squared multiplying I. Remember, this has an exponent of 1, so indices, if you add, you get I cubed, right? Okay. So we know that I squared is -1. We are multiplying it by I. -1 times I is just -I. And remember, this is the same as writing 0 minus I. So in the coordinates form, we can write the real part, which is 0. The complex part is we just have -1. So this is what we have. Okay. So for the third question, we have I to the exponent of 14. One thing that you have to note over here is that we can use the cycle property. We have something that we call the cyclic property. So let me do that quickly right here. So we have cyclic property. For the cyclic property, what it says is that you know I to the exponent of 1 is I, right? I squared we know is -1. I cubed we know is -I, as we've established. Now I to the exponent of 4 is +1. So if we move on to I exponent of 5, what do we get? Remember, I exponent of 5 is the same as writing I exponent 4 times I. I exponent 4 is +1, multiplying that by I, we just have I. So we see it goes back to this right here. So what this states is that whenever we get to I exponent of 4, it moves back. So that is the cycle, right? So if you have I exponent 14, to simplify this, all that you have to do is to first of all divide 14 by the cycle. In this case, we have 4, right? If we divide, you are going to have 3, then remainder what? Remainder 2. So we can represent I to the 14th by I exponent of 4.3 plus a remainder. This 4 times this 3. Now, indices, right? This can be represented as, you can have I exponent 4 cubed multiplying I exponent 2 from indices. Now in this case, I exponent 4, we know that it is equal to 1. So we can have 1 exponent cubed multiplying. Now I squared is the same as -1. Now any number, 1 raised to the power any number is 1, right? So we have 1 multiplying -1, and this is just -1. So if you want the coordinate form of it, this is -1 plus 0i, so you can have -1, 0. So please pay attention to these numbers that we have over here. Okay, and now we've gotten this. Okay, so let's go ahead to find the D. I exponent 25. So to do that, first of all, divide 25 by 4, and you're going to get 6, remainder 1. So you can write this as I to the exponent of 25 to be I multiplying 4 by 6 plus 1. That is I exponent 4, then the 6 outside, times I exponent 1. I exponent 4 is 1 over here. Then to the exponent of 4 multiplying I. 1 raised to the power of 4 is 1. Multiply that by I, you get just I, which is the same as 0 plus I, right? So the coordinate form is 0, 1. Okay, so we also have this. Now let's go to the next one. For E, we have I exponent to 8. So the same idea, divide this by 4, and this is 7 remainder 0. So I28 is just I raised to the power 4.7 plus 0. And this is I exponent 4. You can bring the 7 outside, multiply by I to the exponent of 0. Now I exponent 4 is 1 to the exponent of 7. Any number to the exponent of 0 is 1. So this also simplifies to 1. And 1 to the exponent of 7 is 1. You multiply by 1, you still get 1, which can be written as, you can have this as 1 plus 0i, which is just 1, comma 0. So now we've gotten this 5. Okay, let's look at the last two. So now f. For f, we have I exponent 3, 1. This is 3, 1 divided by 4. And that's going to give you 7 remainder 3. So I 3, 1 is just I exponent 4 multiplying 7, then plus 3. So that is I exponent 4 times 7 multiplying I cubed. And we know I exponent 4 to the power 7. This is always 1, right? So we have 1 here. And what is I cubed? I cubed that we know is negative I. So we have negative I here. So this is just negative I if you multiply these two. So if you are to represent it, you have 0 minus I. And we know that this is just 0, comma minus 1. Okay, let's look at the last one. So for G, we have I to the exponent of 1985. So we have to divide 1985 by 4, and that is going to give you 496 remainder 1. So in that case, we have I to the exponent of 1985 to be equal to I raised to the power 4 times 496, right? Raised to the power 496, right? Then multiply by I to the exponent of 1. Remember, this will always give you 1. So you have 1, then this is I. So you just have I. And this is the same as writing 0 plus I, which is the same as writing 0, comma positive 1. So we have these 6 coordinates. So now let us represent it on the Argand diagram. So on the Argand diagram, we have, this is not drawn to scale, we have 0, 1, 2, and 3, 1, 2, and 3, negative 1, negative 2, negative 3, negative 1, negative 2, and negative 3. So looking at the first one, we have negative 1, 0. Negative 1 is right here. Negative 1 is this, and 0 is here, right? So we can have negative 1, 0 here. This is negative 1, 0. Now for the second one, you have 0 minus 1, and 0 minus 1 should be here. So we have 0 and minus 1. For the next one, we have negative 1, 0, which is what we've done already. Now the next one is 0, 1. So for 0, 1, where are we going to write it? 0, 1 should be here. So we have this. So this is your 0, 1. And the next one is 1, 0. So this is 1 and 0. So we have, we have 1, 0 here. Okay, now let's go to the last two. The last two, we have 0, negative 1, and 0, negative 1. That is what we've already plotted. And the last one is 0, 1, and 0, 1 is what we've already plotted. So this is how our Gantt diagram is going to look like. So it passes through this, comes over here, then it moves in this direction, passes through this, comes here, and comes here. So I hope this explains the concepts. Now, the conjugate of a complex number is really fascinating concept that connects algebra and geometry in meaningful ways. It does not only simplifies division and helps us find the modulus, but it also reveals the inherent symmetry of complex plane. As you continue to work with complex numbers, you will see just how often the conjugate comes into play. In the next video, I will explore the modulus of a complex number, trying it to real-world applications and geometric insights. Thank you for watching, and if you found this video helpful, don't forget to subscribe, like, and leave a comment with your thoughts or questions. I'll see you next time.